Okay. Hello, everyone. Do you have any questions? And, uh, maybe about the problems, because you told that you have some questions about these problems, right? Uh,
Yes, I have one question, but can I show it to you at the end of this lesson?
Okay. Yeah.
Okay, thanks.
Hmm? Uh, hmm?
So
Hmm.
if it needed too much time, I prefer to show the exercise at the end,
Mm-hmm.
not
Yes.
waste the time for the lesson.
Mm-hmm.
Okay, thanks.
Yes. And by the way, I've added some problems to that list, and also wrote solutions, maybe of half of them. So that file is updated. When I finish doing this, probably I'll send an email to everyone saying that some new problems. And there is also a file from the last year. It includes some topics which were not covered this time, or almost not covered, but you can also solve that problems. So, that one contains solutions. Probably some of them are with mistakes. I don't remember precisely, but well, not solutions, but mostly the answers. Mm. Okay, so today I would like to start the new topic, which will be a kind of practical application of this Storm-Liouville theory. So the topic is Bessel functions. So uh, uh, mm, uh, some time ago, we studied the separation of variable for Laplace operator. And, let me write these two Laplace operators for 3D and for 2D. So for d equals 2, Laplace operator written in polar coordinates is d2 over dr squared plus 1 over r d in dr plus 1 over r squared d2 in d phi squared. And the question for d equals to 3 is 2 in dr squared plus 2 over r d in dr plus 1 over r squared angular part of the Laplacian. This angular part is probably better to write on the line. So, like this, and we want to separate variables in a sense to diagonalize this angular parts of Laplacians. So if so we want to find an eigenfunction of a Laplace operator, which is also the eigenfunction of its angular part. Uh, that Laplacian acting on f equals to minus lambda f, and also it's the eigenfunction for Laplacian theta phi, if we have any, if it is a three-dimensional case. So, do you remember what are the possible eigenvalues of this angular part of the Laplacian? What are the possible value of its eigenvalues? So, some number times f. So what should I write here? Like what can I write here? What kind of eigenvalue? So if I add some index to this f, some L, M, K. So uh, maybe there is a simple question. So if you want to diagonalize a d in d phi operator or minus I d in d phi operator, what can be this eigenvalue? D in d phi f equals to what times f? What are possible eigenvalues of minus I d in d phi? Hmm? Yes. So, so this f is e to the I m phi. It is a periodic function of phi as it should be, because phi is just an angular coordinate. I m phi. Hmm. So this eigenvalue we know, but what about this eigenvalue? So there was this equation which is solved by associated Alexander functions. So, but what is the eigenvalue? Yes, thanks. So if if you ask what is the way to remember it, one possible answer is to say that we can act on this operator on a function r to minus L. So if we differentiate such a function twice, we get precisely L times L plus 1, because solution of the Laplace equation uh, uh, in mnemonic rule, f, which is a sum of mm, r to minus L times p L m e to I m phi, some maybe r to minus L a to m is a solution. So minus L minus L plus minus L minus 1 probably. Yes. Actually, hmm, maybe better to say r to power L. Better to consider this solution. Hmm. Let us use some other function of f plus n of f equals to 0. And then we take this r to power L, and mm, and so d r squared r to power L times plus 2 over r dr r to the L is what, it's L minus 1 plus 2L. So it's L times L plus 1. So this number coming from derivative of the radial part compensates the eigenvalue of this angular part of the Laplacian.
So, in the mnemonic rule, what is the relation between the sum and the element?
Uh,
What's the relation?
8R.
Okay.
So and how to remember that this is a solution of the Laplace equation. This precise power should be here. Because you can remember that coordinate functions solve this equation. So, for example, r times cosine of theta is a solution. So the power of r is equal to power of Legendre polynomial. This was precisely the derivation of this number, but you can remember it, I think, because it is a quite simple formula, especially if you remember about L equals 1 case. Mm.
So
Mm.
a n is a coefficient.
Yes, another letter. So. Mm. Even we can remember this formula even in this form without m, because this eigenvalue does not depend on m. It's same for all m's. So for mnemonic rule, maybe it's even simpler to write it this way. without this exponential, simply this expression. Uh, so if you want to remember some function of L, then we can simply cosine of theta. We can remember this. And plus the fact that for L equals to 1, it is r cosine of theta. So it is a function z, and the second derivative in z kills it. So it's actually a solution of this equation. Yes. So we are looking for such a function that is the eigenfunction of the smaller operator and of the full Laplacian operator. So if we solve that equation, we get that for d equals to 2, this we will have simply fmk. It will equal to im phi times some f k of r. So and this function should be found. And for d equals to 3, f m l k will be a product of some eigenfunction of well, let us write it explicitly. It will be im phi p l m, absolute value of m, of cosine theta times some fk of r. So it's the last number that encodes. So let us add this index here. It is some number that encodes the eigenvalue of the full Laplacian. And and this functions AFK will solve some ODs. So, and let us see what precise OD is. So let us take d equals to 2. Well, this last part, or this first part was e to im phi is the eigenfunction of d in d phi squared. So our equation becomes d2 in d r squared plus 1 over r d in dr minus m squared over r squared, acting on f k of r equals to minus lambda r, f k of r. And for d equals to 3, it is d in dr squared plus 2 over r d in dr minus l plus 1 over r squared k of r equals to minus lambda r f k of r. Right? So this is called the Bessel equation. And let us maybe use some different notation for these functions for d equals to 2 and for d equals to 3. So formally, it looks like we have two different equations for different cases. But now I want to show that this d equals to 3 equation can be reduced to d equals to 2. So it is also a Bessel equation. And the only thing we need to change is this coefficient in front of d and dr. And so informally it looks the following way. We have some second order derivative, and then first order derivative with different coefficient. And if you want to change this coefficient, we can shift uh, we can shift d in the r derivative by some function of r, basically by 1 over r with some coefficient. And such a shift is performed by multiplication by some power of r of this dependent function f. Uh, and so let us do this. So let us say that f k tilde is r to power a times k, k of, fk of r, some different function. And let's compute its second derivative. And let us also multiply it by r2 minus a immediately. So the first term is when we differentiate r to the a twice. It will be r to a minus 2. So it will be r to minus 2, a times a minus 1, k of r, plus twice on the term when we differentiate this and this, plus 2a r inverse dr f k of r, d in dr, and plus the term when we differentiate of k, plus this, and then for the first derivative, maybe already coefficient 2. Uh, so we can also multiply it by 2 over r, since we have it in the equation. So then it becomes, and also good factor of 2, 2r minus 2, 2 over r, t in the r, fk of r. So now the question: what value of a should we choose to get this equation? So we want to sum these two terms. How to write this? Like, we want to sum this, and what should be the value of a if we want to recover this differential operator? What's the problem? We are fighting this term. Original equation for d equals to 2 had the coefficient 1 over r. This equation has coefficient 2 over r. So the now we have this transformation which can in principle shift this coefficient by something. So what should we choose to get coefficient 1 over r when we take sum of the two terms? Yes. And so this way, this term becomes minus 1 over r d in dr f k of r, and this cancels this 2 over r. So it gives the previous case. We only need to compute the coefficient in front of 1 over r squared. So we will see what it equals to. And of course, we had another option. We could choose a equals to minus 1, and in this case, we would reduce to kind of one-dimensional problem without this first derivative, but with some 1 over r squared corrections here. So it will not be the usual one-dimensional problem. So it would work only if L equals to 0. Okay, but if a equals to minus 1/2, let us compute the sum of these two terms. So it tells us that r minus a d2 in dr squared plus 2 over r. So r to 1/2, 2 over r d in dr acting on r minus 1/2 fk of r is what? So first take sum of these two terms. This is L times this is A times A plus 1. So it is minus 1/4. Minus 1/4 fk of r, and then plus 2 plus 1 over r d in dr fk of r plus d2 in dr squared fk of r. So there is this transformation on this operator. So if we add the last term, then we get an equation on fk of r of the following form. So d2 in dr squared fk of r plus 2 over r, 1 over r d in dr fk of r minus, so now we combine this minus 1/4 with this minus L times L plus 1. So a full square, so it is L plus 1/2 squared over r squared fk of r equals to 0. So the only difference from the 2D case is that the index of this equation or index of Bessel function, which will define later, is shifted by 1/2. So in the 2D case, this parameter was some integer number. In the 3D case, this parameter is a half integer. but equation is the same. So the only difference in this parameter. So, and this is essentially the Sturm-Liouville problem, because this equation can be written, for example, as 1 over r d d in dr uh, r times df in dr mm, minus, well, we can write it like this. Mm, or maybe it doesn't matter. Mu squared over r squared f of r equals to minus lambda f. So this coefficient is w, this coefficient is p, this coefficient is q, and so this is some Sturm-Liouville operator. And concerning the boundary conditions, it depends on our problem. So in principle, if we solve some problem in a disk or in a ball, then we can fix some boundary conditions there. So we can ask this function to be zero at the boundary. And such boundary conditions are very easily imposed in spherical or polar coordinates. So we can study something like this. F of r equals to 0, or dr, f of r equals to 0, because this such kind of boundary conditions are independent on theta and phi. And so these boundary conditions can be chosen in this way. And there is another boundary condition at 0, and this boundary condition is simply that our function should be regular at 0, because function p, which appears in the Sturm-Liouville problem, has 0 at 0. So this on the left end of the interval has this nature. Another end can be analogous to all these problems with vibrating string. But before going to this special boundary conditions, let us simply learn how to solve this equation, like how to write some solutions, and then impose some boundary conditions. And to find the solution of this equation, I want to propose the same trick as for spherical functions. So, namely, let us study the following function. E to I k y. On one side, this is the eigenfunction of the Laplacian. So, and what is the eigenvalue of Laplacian acting on it?
minus k2.
Mm-hmm. Thanks. Into I k y. So this is on one side. On the other side, e to I k y equals to e to I k r times sine of phi. And so it's some function of phi, and since so it is some function of phi at a fixed k times r. So we can say that this function can be expanded in a Taylor series. So we can write that this e to ik r sine phi is a series over integer n's. So here we simply write some function of kr. So they appear only as a product, and we call these coefficients jn's. Jn of kr, jn of kr times e to I and phi. So it's kind of by definition. I don't know where to put this as semicolon. Mm. Uh, so if you want to write some kind of integral representations for this GNs, how should we do this? Mm. So Jn of kr is what? What do you think? How to write the inverse Fourier transform in such situation? So what should you do with this sum to take just one term? Okay, what is the logic? For example, if you want to take J0, what can we do? What kind of integral can we compute such that all the terms vanish except for the one with n equals to 0? So it is some integral in phi. Oh, of what and in what on what domain? Mm-hmm. Yes. And what should be the integrand? So if you want to get J0, so to start with, what should we put there? Simply using this definition, like how, what should we integrate to get just one term of this sum, and all other terms vanish after the integration. Mm-hmm. Yes, so I, K, R, sine of phi. So we have this is series, and so if we integrate e to I and if we integrate e to I and phi from 0 to pi, it is what? It is e to the 2 pi I n 2 pi n minus 1 over I n for n different from 0. And we should also divide by 2 pi because for n different from 0, it is 0, and for n equals to 0, integral from 0 to 2 pi, dphi is 2 pi. Uh, so we divide by 2 pi. Yeah, so it's for J0. And what happens if you try to compute arbitrary J? So what should be changed? Mm-hmm. Yes, thank you. Uh, uh, yes, and this prefactor simply changes, simply shifts this sum and makes nth term the term which is proportional to constant. So, and all other terms are still positive or negative exponentials, and because of this, they vanish. So, it is the definition of Bessel functions for integer n's. So, the definition. N is integer, j n of kr, Bessel, are Bessel functions. Uh, Yes, so far we just defined them, but now we need to ask what kind of equation is solved by them. So we know that this sum is the eigenfunction of the Laplacian. So and this exponential e to the I and phi is the eigenfunction of id in dphi, precisely with that eigenvalue n. So we can write that Laplacian acting on the sum sum over n integers jn of kr e to I n phi equals to minus k squared. Well, better to write it like this. Laplacian of j for this equals to minus k squared sum. And now let us simply act by this Laplacian. So we get d in dr, d2 in dr, plus 1 over r plus minus n squared over r squared. All this acts on jn of kr. Sum over n integers e to I n phi equals to minus k squared. So and now we can simply take all the terms in front of different exponentials separately. So we say 1 over r d in dr. So we see in this equation d in dr squared. Maybe better to multiply everything by r. Let me write it like r squared d2 in dr squared plus r d in dr minus n squared plus k squared r squared jn of kr equals to 0. Right. And now we see that kr appears as a single object as inside the argument, inside this equation. So we can simply write an equation in this argument in kr. Or in other words, say that k equals to 1. So we have this equation r squared d squared in dr squared plus r d in dr minus n squared plus r squared acting on jn of r equals to 0. So this is called the Bessel equation. So, and as before, as for the spherical functions, we already know the solution of this equation. And so far, actually, we know only one solution because because this is something that is regular around 0. And as we remember from this Sturm-Liouville story, and the second solution will be something that has singularity at r equals to 0. So it is not nice if you want to find some regular solution of Laplace equation, but in principle such function exists, and we will find some way to also to write that function. So are there any questions about this?
So I have a
Mm-hmm.
question. I don't remember if you already said it, but the scri n of k r, can we see that the Fourier transform of the function e to the ik blah blah on the disk or no?
No, but it's not on a disk. It is a Fourier transform only in phi.
Oh, okay.
Oh.
Okay.
And concerning the Fourier transform, let me think if I'm ready to tell this. Mm, moment. Actually, I wanted to tell something about the analog of Fourier transformation using this Bessel function, but I'm not sure that this computation will work, so probably I'll do this next time. And now let us study some properties of these Bessel functions. Mm, let us start from some simplest formula, namely, let us try to compute the Taylor series of J0. So, uh, mm, series expansions. So let us start with J0. It is the simplest function. So J0 of R is 1 over 2 pi, integral from 0 to 2 pi, d phi e to I k, so e to I r sine of phi, or simply this. And to find this, we can write this exponential as a product of two exponentials. 1 over 2 pi, integral from 0 to 2 pi, d phi e to 1 half r e to I phi e to minus 1 half r e to minus I phi. So now we can expand each of these exponentials as a Taylor series, because in any case it will be some series in R. So it's integral from 0 to 2 pi d phi sum from n equals to 0 to infinity 2 to minus n r to n e to I phi sum from m equals to 0 to infinity to minus n r m r m e to minus I n phi minus I m phi. And so what terms in the sum can survive? What will get after the summation? And of course, I forgot to divide by factorials, n factorial and m factorial. What will be non-vanishing contributions from this integral? And I also forgot minus 1. It's minus 2 to minus m. Yes. Mhm.
Maybe for n different to n,
So what will happen to them?
they goes to a delta.
Oh, so the surviving terms will be for m equals to n, right? Because if m is different from n, it is some exponential with non-zero argument. It vanishes. And if m equals to n, these two exponentials cancel, and we integrate 1. So it is sum from n equals to 0 to infinity. Uh, uh, Minus r over 2 to power n minus 2 to power, so minus r squared over 4 to power, or maybe better to write it as minus 1 to power n r over 2 to power 2n times 1 over n factorial squared. Right? So this is n factorial squared in the denominator. So this series is very similar to another series. Maybe we can consider cosine of r over 2. And this one will be sum from n equals to 0 to infinity, minus 1 to n, r over 2 to 2n. And what else should be written in this formula? Well, it's kind of 1/2 of an exponential. It is 1 over n factorial. So Bessel functions are kind of is similar to trigonometric functions, but with double factorial, no, squared factorial in the denominator. And if we draw a plot of this function, then this one looks like this. It will be something, and it's not periodic. So it goes to 0 like 1 over r. It is symmetric. This is d0 of r. And here it is just a periodic function. Well, it's a very bad picture, uh, but I think everyone knows how a plot of cosine function looks like. So they both equal to 1 at 0. Mm, they both oscillate, so they have a lot of zeros, infinite number of zeros. Uh, but other properties are different. And for example, if you want to solve such kind of problem in a disk, we can adjust the Bessel function of Kr such that it vanishes on the boundary. So if it was a one-dimensional problem about a vibrating string, then we had to look for zeros of some sine or cosine on the other end of the interval. In this case, the trigonometric functions are replaced by a Bessel function, and so if you want something like this, then we should solve Jn of k times r equals to 0. So there will be formulas like k equals to uh, mm, so how to denote zeros of Bessel function. Mm, and z ends over over r. So I don't know if there is some canonical name, but we can write that there are some zeros. They can be found anywhere, I think. And also, if we think about these properties of Sturm-Liouville eigenfunctions, then uh, we clearly see that since a solution of the equation is just the Bessel function of a scaled argument, then changing the eigenvalue is simply a scaling of Bessel function. So it is the same in this plot will have the same shape, but mm, a little bit scaled in this direction. So. Mm. So there is this series, and let us also study some other series, namely the series for generic Bessel function. So are there any questions about this or not? Hmm?
Can you repeat what's happened to the sum over m?
But integral of integral from 0 to phi e to I n phi e to I n phi 1 over phi. What does it equal to? Mm. So it's delta and n.
Okay, so you have to use rule to
Ye-
get the
ye-
okay.
Yes. So. Mm, mm. So now we can erase this. So the only thing we need to remember is that these Bessel functions that appear for a spherical problem are Bessel functions with half integer index. And so far we only have Bessel functions with integer index. Mm. So let's erase. Let us first study some property of this Bessel functions. Namely, let us study the relation between n and j minus n. So j minus n of r is 1 over 2 pi integral from 0 to pi d phi e to minus e to k I sine of phi e to I and phi. So we change the sign here. And I would like to write it in some form that produces Jn back. So, so we don't want to modify this part, but we want to change sign in this exponential. So it can be done by symmetry. Phi equals to pi minus phi tilde. On this way, sine of phi will equal to sine of phi tilde, because sine has this symmetry. So, and here, yeah, so it will be 1 over pi integral from 0 to 2 pi as before. Now d phi tilde e to I r sine of phi tilde e to I phi n e to minus I phi and phi tilde. So it is e to I phi n. Well, let us simply write a minus 1 to the n, minus 1 to the n, and jn of r. Okay. So there is such a symmetry in index. And this symmetry can break our naive hope that since this equation depends on n squared, not on n, we could obtain another solution by changing n to minus n. So it shows that jn and j minus n is almost the same up to sign. So it was simply a property of this kind of labeling, but not of the individual function. Let us study the properties of Jn as a function of R. Namely, let us look at Jn of minus R. In principle, we see that J0 is some even function. So it has even powers of R, and we want to show that other Bessel functions are also odd or even depending on index. So Jn of minus r is 1 over 2 pi, go from 0 to pi, d phi e to minus ir sine phi e to minus I n phi. So now we would like to change sign of a sign of this sign. So, but sign of this exponential, well, if we don't change, Okay, we can change sign of this exponential. So let us say that we are changing phi to minus phi here simply. So this will turn this integral into this integral. So it will be j n of r, j minus n of r. But using the previous computation, we can write that it is minus 1 to the n and jn of r. So odd functions are odd, even functions are even. So there are such simple properties. But now let us do something less trivial. Okay, so well, we also need to compute series expansion of this function. So let us do this. So j n mm, of r. Let us say that n is positive for the yes. So in symmetric, so we can say that n is positive for simplicity. So this function equals. I will use the same idea and simply add another factor that corresponds to exponentially to minus I phi. So it will be 1 over 2 pi, integral from 0 to pi, d phi, sum from m equals to 0 to infinity, to minus m r to m e to I m phi 1 over m factorial, and here it will be sum from m prime from 0 to infinity 2 to minus m prime r to m prime e to minus I m prime phi 1 over m prime factorial. So this is precisely this part, but we modify our original integral by this extra factor e to minus I n phi. So we add it here, e to minus I n phi. Yes, so now this computation modifies a little bit. So we will have a delta function of m, comma m prime plus n. Maybe it's better to change m and n prime. Yeah, maybe it's better to write like this. Like this. And probably can you write the answer immediately, or is it better to do this intermediate step? Maybe I can ask you, what kind of answer will we have here? I also forgot some minus 1 to m here, because on that second term had minus sign. Yes, so can you tell the formula which you get after the computation? So let us say that the sum is the sum will be in M from M equals to 0, from M equals to 0 to infinity, and so the first question, which terms in this sum will contribute to the answer? So what are the non-vanishing terms? What are the conditions for M, M prime, and N? Hmm? No, there is another exponential. When we integrate this, we have a product of three exponential with M prime, with M, and with N. So the idea is to express M prime in terms of M because well, the range of two variables is from 0 to infinity. So so what will be M prime in terms of M? So mm-hmm. Yes. So yes. So otherwise, we have a non-zero argument of the exponential, and this integral simply vanishes. And if we write like this, n is something positive, and it is fixed. So m goes from 0 to infinity, and m prime goes from n to infinity, because well, there are some other terms, but they cannot satisfy this condition. So writing like this, we can express this. We can reduce this double sum to a single sum in m, right? So the only term will lie on this shifted diagonal. M prime equals to m plus n. Everything else vanishes. And now we simply write these terms. So it will be 2 to minus m plus n, r minus m minus n, minus m minus n, r to m plus n, 1 over m plus n factorial. It's from the first exponential. And from the second exponential, it will be minus 1 to the m, 2 to minus m, r to m, 1 over m factorial. So in total, it is a sum from m equals to 0 to infinity, minus 1 to power m, r over 2 to power 2m plus n, 1 over m factorial times m plus n factorial. So this is Jn of n. So are there any questions about this computation? But, so say for example that odd j's are odd simply because the series contains odd powers of r. So the leading power is n, and all other powers are shifted by 2. So, and we also see that Jn of r behaves as r to the n when r goes to 0 from this series. So they have a 0 of nth order at the origin. And this is already different from behavior of trigonometric functions. Yeah, so we have this series, but we still have a question how to solve this differential equation for arbitrary n. And once we obtain this series representation, we can try to write some function that is valid for arbitrary n. Namely, we can perform analytic continuation in n. Yes. So, and let us do this. So we replace n with some a number with some letter nu, which is just some arbitrary complex number. This is a standard notation for the index of Bessel functions. And let us define J nu of R by this series. J nu of R is the sum from m equals to 0 to infinity, minus 1 to m, uh, R over 2 to m plus nu. And here, one factorial survives, and another factorial should be replaced by a gamma function, m plus nu plus 1, because it is and the analytic continuation of factorial. So it is the definition. So there is such a series. And we can see, for example, that this series, there is no symmetry between nu and minus nu for arbitrary nu. So J nu in general is not proportional to J minus nu. And in particular, what are the asymptotics of J nu of R when R goes to 0? So what happens when this series? So we simply have some term at m equals to 0, and this term has a 0 factorial and gamma function of nu plus nu plus 1, which is in general situation nothing special, just some number. So it is proportional to R2 minus nu. So since asymptotics of J nu for positive and negative nu are different, we will not have this equality for arbitrary nus. And now these two functions are really linearly independent. So if you want to write a second solution of our Bessel equation for arbitrary nu, we can simply take J nu and J minus nu. It's one option. So for non-integer news. And by the way, Is it clear what happens for integer news? We know that if this index is integer, then this Bessel function coincides with Bessel function with opposite index up to the sign. Is it clear how it happens technically in this series? For example, I don't know what is a 1 over gamma of 0. Mm. In general, about the gamma function. So, gamma function has this current relation, gamma of x plus 1 equals to x and gamma of x. So it's like for the factorial. And in particular, I can reverse on this relation, saying that gamma of x minus 1 is 1 over x minus 1 and gamma of x. So gamma of x minus n equals to 1 over x minus n, and so on, 1 over x minus 1, gamma of x. And for example, if x goes to 1, let us substitute x equals to 1 plus epsilon. Then gamma of 1 plus 1 minus n plus epsilon will be 1 over 1 minus n plus epsilon, and so on, 1 over minus epsilon, gamma of 1 plus epsilon. So we see that there is a pole at epsilon equals to 0. So gamma of 1 minus n plus epsilon is proportional to what? To minus 1 to the n, I think. Yes. N or n minus 1, or maybe minus 1 to the n over n minus 1 factorial times 1 over epsilon. So a gamma function at 0 and at all negative integer values vanishes. So if we substitute nu equals to minus integer, then it kills first something like n or n minus 1 terms of this series, and the first term has a positive power of r. So, and we can probably, we can prove that it will be the same function. So, another way to understand that gamma function has poles at or negative numbers and 0 is to use this reflection relation, pi over sine of pi x. So we know that if x is positive, then this positive and integer, then this function is just factorial. So what is the origin of poles? They can only come from gamma of 1 minus x. And you can also get this asymptotics from this formula. Yeah. Yeah. Yeah, but we have this formula, and in particular we can apply this for half integer news. And it turns out that if nu is half integer, this sum can be computed explicitly, and it is expressed in terms of trigonometric functions. So. mm, Last time I derived this formula, but maybe it is not very good exercise to do here. So we can simply open Wikipedia, read about spherical Bessel functions, which is precisely a Bessel function with a half integer index. Find some formula for it, and then think how to prove it, starting from this. So the main idea is that if we have gamma of x times gamma of x plus 1/2, it can be written as gamma of 2x. Yes, times something. So using this, we can obtain the formula for half integer j's in some explicit form. Yeah, but let us study this Bessel function with arbitrary index. So if this index is integer, we have this integral representation. But our definition of this Bessel function is written in terms of series. So we would like to have this integral representation back. And there is one technical technical trick that allows to construct integral representations from series. So the trick is the following. So everyone knows that there is a representation of the gamma function of this form. Gamma of p is the integral from 0 to infinity dt e to minus t to p minus 1. Oh, and this is valid for some p's such that this integral is convergent. So they cannot be too negative. But there is also another representation of gamma, namely of inverse gamma. This representation looks like this. So and the integral goes around the negative half axis. So then this integral, and here we have dz, z to minus s times e to tz. So this function z 1 over pi I. So this function is well defined for a positive z. It is simply power of a positive z. And if we go here, we need to perform analytic continuation in this direction and in this direction. So it will be a kind of the same function with different with different mm, mm, argument, e to the pi I s and e to the minus pi I s. So, so it's another representation. And let us study some special cases. So, namely, examples, s equals to n plus 1, and n is integer. So, so this formula, maybe just one example, this formula tells that it is 1 over 2 pi I. Oh, sorry, I wrote some t. No, simply z. So it tells that 1 over n factorial is the integral uh, around. So here, this contour is simply the contour around 0, because this function is a single valued when s is integer. So it's simply a contour around 0, dz over 2 pi I z to n plus 1 e to z. So is it clear why this integral equals to 1 over n factorial? And that 1 plus z plus z to the n over n factorial plus, right? So, so is it fine? So the only term is this, z over n factorial, and this is the rule how to remember such kind of formula. Always think that we want a formula that gives 1 over n factorial in this way, and then take analytic continuation in n to arbitrary s, and since this function becomes non-single valued, then we have such kind of an integral. And now, actually, it's not a proof that it is 1 over gamma function. We would also like to show that it coincides with the gamma function for s for such s that this integral can be written as the integral over this negative line, so that it does not have a singularity at 0. It is convergent in 0. So, and it happens when a real part of S is something like less than 1. So we can square this contour to the imaginary line, or to the negative real line, and write that 1 over gamma of S is the integral from from 0 to infinity, and here we write some variable t minus dt times t. So we have two parts, for the upper contour and for the lower contour. For the upper contour, phase of z to minus s will be t to minus s times e to the plus minus 2 pi I s. E to minus t. It is one integral. Another integral will be over the negative, over this part of contour. And this will be plus integral from 0 to infinity dt t to minus s times e to the 2 pi s e to minus t. Right. So is this clear? So one exponential comes from analytic continuation in the counterclockwise direction. Another comes from analytic continuation in the clockwise direction. And this dt corresponds to integration in the negative direction, and this plus dt corresponds to integration in the positive direction. So here z was increasing, here z was decreasing. So this can be written as and there is also our factor 1 over 2 pi I, and here as well. So these exponentials together with 1 over 2 pi I can be combined into sorry, it is not 2 pi I, it is simply pi I, because I integrate because it is analytic continuation only by pi. So this can be written as a sine of pi s over pi times the integral from 0 to infinity dt t to minus s e to minus t. So this is mm, uh, so what kind of gamma function do we get here? So what is this? So it's sine of ps over pi s over pi times gamma of what? No, one minus s because mm, so so it is a typical situation when we have some function with a branch cut that integrals around this branch cut can be computed this way. So we see that this integral, which should represent the gamma function, has this formula. And so far we actually don't know this relation between gamma of x and gamma of 1 minus x. And if we want to establish it, we need to remember the relation to beta function. Uh, so mm, so there was this formula that uh, gamma of x times gamma of y equals to beta of x y gamma of x plus y, and beta of x y was the integral from 0 to 1 uh, t to x minus 1, 1 minus t to y minus 1 dt. So we can use this formula for s and 1 minus s, gamma of s, and gamma of 1 minus s. And this equals to beta of s 1 minus s times gamma of 1, which is 1. And if you want to compute a beta of s and 1 minus s, then it can be done like this. Maybe beta of 1 minus s, s, no, beta of s, 1 minus s is equal to integral from 0 to 1, uh, t over 1 minus t to our s dt over t. So this integral is the integral around the contour from 0 to t. Like it was the integral a little bit about this contour, and this contour from 0 to t has the branch cut. So if you want to compute this integral by residues, we can complete it to the integral around the contour. And when we perform this analytic continuation, we will add some phase. Namely, when we turn around 0 in the counterclockwise direction, so we would like to add another integral like this. So when we turn around 0, it will get this will get another exponential like e to the 2 pi I s. So we can write that this integral equals to 1 over 1 minus e to the 2 pi I s times integral around this contour C, times integral around this contour in the clockwise direction. T over 1 minus t to s dt over t. And now, once we have this, we see that when we send t to infinity, this function will behave like minus 1 to the s times t over t. So we can shrink this contour to infinity, and this way compute this integral. So in principle, we should take care about this phase when t goes to infinity. But let us simply trust me that this phase is e to the plus pi I s. So this integral will equal to the integral e to the pi I s over 1 minus e to the 2 pi I s. And let us also inverse this contour. So let us put here minus 1. So this integral will be around this contour, which is counterclockwise. T over t minus 1 power s dt over t. So now we're pushing this contour to infinity, and simply write that it is 2 pi I. So it will be 2 pi I over e to the 2 pi I s minus e to the minus 2 pi I s. So it is simply pi over, pi I s minus pi I s. So it is simply pi over sine of pi s. So the end of proof. So it's basically the same argument that was used to compute that integral. And if you compare it, we can say that this sine of pi s over phi times gamma of 1 over s is 1 over gamma of s. Actually. So this was a kind of rigorous proof that if we define gamma function as the analytic continuation of something defined by this integral representation, then this is another integral representation for 1 over gamma of s. And the advantage of this representation is that it is valid for any s. Because here we should care about convergence of this integral, but this function, this integral is always convergent because this integration contour does not touch 0, and the exponential of z is greater than any power of z when z goes to minus infinity. So it is more convenient, and it is also convenient for such for transformations of such kind of series to integrals. And we will do this next time. So, do you have any questions? If no, then Thanks for your attention. See you tomorrow.